Thank you so much for joining. My name is Andreas Kopp. I'm a cloud solution architect from Microsoft, responsible for delivering customer engagements based on our AI platform. Together, I have my colleague Harmke Alkemade from the same team and Kristopher Kersten from NVIDIA. And we would like to show you how you can leverage Azure Machine Learning and NVIDIA Flare for privacy preserving federated learning, basically combining three tools: Azure Machine Learning, NVIDIA Flare, and the MONAI framework for medical imaging. So this is the plan for today. We are going to start with an introduction about what federated learning is and how it works. We have a quite interesting medical use case. So this is multimodal 3D brain tumor segmentation, which we are using to compare classic centralized training with federated learning. And finally, you will see it in action by a demo from Harmke. All right, yeah, let's talk about the reasons or the motivation for federated learning. So imagine there is a hospital like the Memorial Hospital. They have collected data points about their patients, and they are interested to train a machine learning model, for example, to predict the effectiveness of treatment. And even though they might have many data points when it comes to rare diseases or to be representative for various parts of the population, when you consider all kinds of combinations between age, gender, ethnic background, for example, or medical preconditions, the data points that are remaining for training the model might be quite rare. So it might be the case that based on the data that Memorial Hospital has, the machine learning model, the resulting model in terms of performance and in terms of accuracy is good, but not perfect. But of course, Memorial Hospital is not the only organization which has such kind of data and has such kind of questions to use machine learning. So we have other hospitals, we have other medical institutions. So, and it would be quite obvious for those hospitals just to combine the data to train a joint machine learning model. And since machine learning typically benefits from more and more diverse data, what could be expected from such a setup would be a model which is better, has better accuracy, and is also more robust for all kinds of, let's say, subgroups. The problem is that even though this benefit is obvious in practice, it often just does not happen because there are compliance concerns due to data privacy, for example, or due to regulation, or maybe there are concerns of sharing intellectual property. So even though there is an obvious benefit of pooling data, it does not happen in practice too often. And this is where federated learning comes in. So the idea here is really to enable multiple parties to train collaboratively without the need to share any data. And the way it works in those enterprise settings typically is that you have a kind of orchestrating institution. This could be one of those hospitals. They provide what's called a federated server, which has an initial model that is distributed to all those participants, to all the hospitals. Then each of the hospitals is performing a local training based on private data, but the data is private, it is on premise, and it remains private, so it is never shared with the other institutions. Instead, what the models, the local models have learned, technically speaking, the weights, they are sent back to the federated server where they are aggregated. Then a next iteration, a next version of the model is generated and is then distributed to the other hospitals. And this happens in several rounds. At each round could be an epoch, for example, and over that time we can expect, and we see it in practice a little bit later, that the model gets better and better, and you can then decide to finish this process, this iterative process, once you're satisfied with the results, but you can also use it for continuous learning. So that's basically on a high level how federated learning works. And the key aspect really is the data is never shared in this process. And in order to show the benefits of federated learning, we decided to use this multimodal 3D brain tumor segmentation use case for two reasons. One, it is from a societal point of view very important because it supports, such use case supports diagnosis. It can be used to monitor the progression of tumors, for example. It can be used for treatment planning or for the monitoring of treatment success. This data set is also from a computer vision perspective quite interesting because we are talking about 3D volumes. So those are stacks of images. For each patient study, we are talking about 155 images stacked together to a volume. And it's not only one stack of images per patient, it's actually several modalities, which means that the MRI device generates those images under different settings. And so we have 4 modalities here, and those different modalities can be used to answer different questions about the images. So for example, with this FLAIR image, this can be, or this FLAIR modality can be used to identify abnormalities in the image, while another modality, for example, what's called D1GD, can be used to identify different regions in the tumor, for example. So that's the input for our model, the features. And then we have expert annotated tumor areas, which are also 3D segmentations, so also stacks of images, which show different areas of the tumor. Once it's the whole tumor, so the whole structure. We also have within the whole tumor, we have what's called the tumor core. That's the solid part of the tumor. And then there is also an enhancing tumor structure. This is kind of a peripheral structure of the tumor core. And this is typically where the most aggressive part of the cancer cells are in this enhancing tumor structure. And this is very important for treatment planning to distinguish between the whole tumor, the tumor core, and this enhancing tumor structure. And with this, I would like to hand over to Chris to explain a little bit what NVIDIA FLAIR is and how it works.
Andreas, thanks for setting the stage. I'd like to take just a few minutes to introduce NVIDIA FLAIR, or our Federated Learning Application Runtime Environment. So over the last few years, federated learning emerged as a great solution for data privacy, initially in the healthcare domain, where patient privacy is a critical concern. But as we built the platform, it quickly became obvious that data privacy and data locality were issues that were not unique to healthcare. These presented problems across industries and demanded a general purpose federated learning platform. So we built NVIDIA FLAIR to be platform and use case agnostic, released it on GitHub under the open source Apache 2.0 license as a standalone platform and SDK for federated learning. NVFLAIR provides a base runtime environment that manages communication, along with reference algorithms for privacy preservation and federated workflows, and a set of tools that allow developers to address issues not just of data privacy, but data locality, where data volume makes centralized storage impossible, or where data is naturally collected in a distributed way, for example, in autonomous vehicles or instrument monitoring. Andreas, next slide. So looking a little more closely at some of the key features of the platform, on the left we see the FL Simulator and the FL Dashboard. These are tools that allow developers to develop and debug federated applications locally, and then seamlessly, securely deploy a federation of clients in a server, and then deploy that same app on a distributed deployment. We also have tools like federated statistics that allow data scientists to understand client data sets in a distributed way, as well as a unified CLI that allows a researcher to manage the clients and applications being deployed in the experiment, as well as the individual sites' fine-grained secure privacy policies. Last, I'd like to highlight our framework integration with community projects like XGBoost and MONAI. We include APIs to quickly adapt applications developed on these platforms to the federated paradigm. To see this in action, I'd like to hand this off to Harmke, who will show a demo of a distributed deployment built on Azure ML with Flare and MONAI.
Thanks, Chris. So with that, let's have a look at the demo to see it all in action. So on this slide, first, I want to introduce the overall architecture of what you will see later in the demo. So in the middle part, you see the federated server. So this server basically serves as an orchestration party to send the training instructions to the different clients. And after they are finished with their rounds, also collects the different local models in a central place and aggregates the weights to make sure that we have one global model to work with. So this federated party is represented in our solution by a data science virtual machine and also by an Azure machine learning workspace that we will use via an orchestration notebook. You will see that in the demo later. And other than this central party, we are working with 4 different clients in this demo setup. We have one client in Europe as well. So this one is using the same machine learning workspace as we will be using for the orchestration. But we also have a couple of different hospitals, one in Canada, one in the US, and one in Australia. So these different clients will be represented by their own machine learning workspace, where we have their own assets that we will be registering for them to work with. So basically, all these hospitals will have their own private data set and will be training their own local models using the compute clusters that are available on the machine learning workspace. So for the data set, we are using the BRADS data set that Andreas already introduced. So the brain tumor data set with the different modalities and the different tumor regions that are annotated. An overall solution is a combination of Azure machine learning. So you will see the different machine learning workspaces in the demo and also the different assets that we are registering there. Of course, we are using NVIDIA Flare for the federated learning part, and we are also leveraging MONAI as a framework for some of the functionalities that we are using in the training pipeline. And with that, let's start to have a look at some of the data visualizations to make it a bit more clear on what is the data that we are working with. So here I'm just visualizing one data point that we have in the data set in this 3D visualizer. And as you see, what we are doing here is that we are basically combining the different data slices that we are working with in order to visualize more like this brain structure of what is actual in the data. And the red area that you see annotated here is the tumor region that is annotated for this specific patient. And to make it even more clear, I will also want to show a 2D visualization of one of the data points in the data set. So in this case, for one patient, we are not looking at all the slices together, but we are just highlighting one of the slices and showing the different modalities right here. So as you can see, we have these different tumor structures that are annotated. So this first one actually combines all the different structures, but we have the tumor core right here. We have the whole tumor, which is a bit of a bigger region. And here we have the enhancing structure as well. So this is basically the data that we will use for the training. And now let's move to our Azure Machine Learning Workspace to look at our training setup. So for this, we will use the notebooks interface within Azure Machine Learning, and the complete workflow end-to-end is implemented via an orchestration notebook that I have loaded here in Azure Machine Learning. So let's walk through all the different steps that we have in it. So I will skip some of the imports and variables that we have defined. And as a first section, I want to highlight the one-time setup steps that we need to basically initiate the overall architecture that you saw on the slides. So the steps that we are performing here as one-time setup is provisioning the NVIDIA Flare startup kits. We are registering the Python environments that we need to make sure that we have consistent environments for training the data set and also for the server. we are downloading and registering the data set, and we are creating the compute clusters that we will be running the jobs. And this image is just to highlight again the overall architecture, but in this case, a bit more from a technical and asset perspective. So within our Europe workspace, what we will have here is a training cluster that we will be using for a central experiment to compare that with the federated experiment later. We have a data science virtual machine. As we mentioned before, this is the one that we are using for the federated server. We have a compute instance that we are using for local development. That's what you're looking at right now. And we have the different data assets and the environment for the training. And on the client side, what we will have for each hospital, we have one training cluster, we have the same training environment to make sure that it's consistent, and a data asset as well. So that is what we will all be setting up here, starting with the Flare startup kits. So if you work with NVIDIA Flare before, then you know that this would involve a project.yaml file, which is a file that basically lists all the participants and also the server that you would have in a federated learning solution. So that is what we have in this solution as well. So here we are listing the server with all the details that are important and also the different clients. And what we did for this particular solution that combines Azure Machine Learning with NVIDIA Flare is that we actually extended this project.yaml file with some of the variables that are relevant. For example, the Azure Machine Learning workspace is one of the variables that we added here for the different clients. So here we are using the provisioning command and this project.yaml file to generate the startup packages that we will upload to the server and the clients later to initiate the federated learning communication. Then we will set up the other assets. We start here by setting up the Python environment. So this is basically a Conda environment that we are defining via a requirements file. From this environment file, we are building a container image that we are then registering to the different workspaces so that we have a consistent environment for training the local models for the different hospitals or clients that we are working with. And then we are downloading and registering the data. So for this, we are directly using the Kaggle API. So it is actually a public data set that we are working with. So we can leverage this API to download the data. And then we are registering it for the different workspaces. And in some real life scenarios, this might be a bit different because you might be working with local hospitals that want to upload their own data assets to the local compute. This solution also supports that, but just for this demo scenario, we decided to register it from a central party. And then the last asset that we need to set up for the different workspaces are the compute clusters. So here again, we are looping over all the different machine learning workspaces, so both the central one and for the different clients, and creating all the compute clusters that we need to do the local training. And with that, we basically finalize setting up all our assets, and we can move on to the next stage, which is submitting the Azure Machine Learning jobs to the different compute targets. So how we will use these jobs is that both for the server and for the clients, we will basically use an Azure Machine Learning job to submit the startup packages to all the parties that are involved. And these startup packages, when their startup scripts are running, initiate the communication between the different parties. So that can be quite helpful. And before we do it in a federated way, we start here by doing a simulator run. So the simulator run is part of the NVIDIA Flare package, and this is a way to quickly experiment with your federated learning code with the overall federated setup. But in this case, we're just using one compute. And in our example, how we are using this is that we are doing a run just with one client, so we can test the performance later on with an experiment where we are using all the 4 different clients that are involved here. So this is what you can see here. We are defining our job commands with the simulator commands that we have defined here and all the different assets that we have created before. So our experiment, our compute target, and our data assets. And then we are submitting the job to the cluster. And after running this, you can see in your central machine learning workspace that there's a job created. And if we go to the metrics section of this job, we can also track the metrics of our experiments. Those are tracked via MLflow, and they are actually streamed to your machine learning workspace while your job is running. So you can track the performance along the go. And also after it's finished, you can have it here for tracking the performance later if you want to compare it with some other experiments. So after we are sure that our code works and we took a look at our performance, now we will do our actual federated run. So for this, we will first start with running the server package inside a container in the machine learning workspace that we are currently looking at. So here we are defining another job, but this time we are submitting the NVIDIA Flare server package to this job to make sure that the server package will be running inside a job in our workspace. And then we are doing something similar for the clients. So here we are looping over the different clients, and then for each of the clients, we are submitting an Azure Machine Learning job with the appropriate client startup package so that we have the appropriate code at the right client, and then we can run the startup scripts to make sure that all the communication is initiated. And after running this and waiting for the clients to be finished, what you will see later is if you look at the logs from a server perspective, is that all the clients basically indicated that they are ready to start with their experiments. So after these setup steps, we are ready to go to start a federated training run. And that's actually the next step. So the final part of this notebook describes how we are using the NVIDIA Flare API runner. So this is the NVIDIA Flare Python package that we are using right here to start our federated experiment. So here we are first connecting to the admin client. So this one is running on our server as well, and we can use it for orchestrating the jobs. We will first run the check status command to check if all the clients are connected correctly. And there you see the 4 different clients here that we are working with. And then the final step is to submit our job to the server that will then orchestrate it to the different clients. And just to highlight a bit on the specific code that we are using in this case, just a quick look at one of the training scripts that we have right here, because this is where we are leveraging the MONAI components. So overall, it would look quite familiar if you're familiar with any PyTorch training script, but maybe to highlight some specific parts, this is, for example, where we are importing the model artifact from the MONAI library. And also for the different transformations, we are using the transformations that are available in the MONAI package, which was quite helpful for setting up the transformation pipeline. So with that, we actually started our federated experiment. And I started an experiment a couple of hours earlier, just to have a look at what we can see while the experiment is running. So here you can see that there's an Azure Machine Learning job that was created in my workspace, which is a server job. And now, while the job is running, we can actually, when we go to outputs and logs, we can check the different logs that are created while the experiment is running. So this is quite helpful because some of these experiments might actually take some time. So it's useful to track while they are running what the status is of your specific experiment. And we can also have a look at the metrics, where we will see an overview of the metrics that are created so far. And this is a bit different to the simulated experiment because now we will actually see all the metrics that are generated by the different hospitals. So the list is a bit longer here. So with that, let's have a look at the results that we have actually created after doing this experiment. So what we did is that we compared a federated training experiment with a centralized training run. We did an experiment of 200 rounds, and the performance is what you see here on the slides. So the blue line here is the performance that we achieved for the distributed setup with the 4 different hospitals. So this is the average performance over the 4 different hospitals that we are working with. And the red line indicates the performance over time for our centralized experiment. And what you actually see here is that overall, over these 200 rounds, that we achieve more or less the same performance. And in our case, performance means the dice metric, but that we needed a bit more rounds or epochs for the distributed run. So that there was a bit of delay in achieving the same performance, but overall we were able to achieve the same dice metric at the end of the training run. So that concludes the demo. And with that, I would like to quickly highlight the medical imaging repository if you're interested to see more content related to medical imaging and Azure machine learning. The demos that are available in this repository are very diverse. So it ranges from custom PyTorch experiments to MLOps experiments, but also using AutoML for images, for example, or using some of the privacy preserving techniques that we also showed today with federated learning. And if you're interested to read more about it, then we also published some articles on Medium that might be interesting for you.
Thank you, Harmke and Andreas, for sharing this great example leveraging these three platforms to address the real-world use case in federated medical imaging. I'd also like to thank everyone else for attending today, and I encourage everyone to visit NVIDIA's Microsoft Build Virtual Showcase, where you can find additional demos and information on this session, information about the NVIDIA Developer Program, along with additional NVIDIA sessions happening at Microsoft Build. Thank you.